Hello.
Good evening, sir.
Yeah, good evening. Everyone can hear me, right?
Yes, sir.
Okay. So we had one problem at the end of last class that we have to discuss. And after that, we'll start the new topic. So this problem was basically remainders were given for a single polynomial, a polynomial f of x. We have to find this polynomial which has two properties. When f of x is divided by x power 100, the remainder is 1. And secondly, when it was divided by x minus 2 whole cube, the remainder is also 1. No, remainder is 2. So we have to find a single polynomial f of x that satisfies both of these situations, both of these conditions. If you haven't tried it, try it right now. By applying the division algorithm, you can say f of x should be some quotient polynomial times x power 100 plus 1. And f of x should also be some other quotient polynomial times x minus 2 whole cube plus 2. These are the conditions that we know.
So, sir, we can say f of 0 equal to 1 and f of 2 equal to 2.
Mhm. See, the problem here is the plus 1 and the plus 2. If we didn't have plus 1 and plus 2 here, you could have multiplied these expressions. So you have to think of what to do to sort of remove the plus 1 and plus 2. So one thing you can try is take derivatives. F dash x will become 100 q of x to the power 99 plus x power 100 q dash x. So from here, we can take x power 99 common. We get 100 q of x plus x q dash x, right?
Yes, sir.
This is f dash x. And from here, also we can take derivative. F dash x is equal to, you're getting 3x minus 2 whole square rx plus r dash x minus 2 whole cube. And from here, we can take x minus 2 whole square common, right? 3 r of x plus x minus 2 r dash x, correct?
Yes, sir.
So from this, we know that f dash x has what factors? This is guaranteed, and this is also guaranteed, right?
Yes.
So f dash x is definitely can be written as some x power 99 times x minus 2 whole square, some constant.
Right.
This this could be f dash x. We have to think about what happens to inside the stuff inside, right? Uh, is there anything else that will come in f dash x? That's what we have to think. So if you have a polynomial f dash x like this, when you think about the next f of x, right? If you think of f of x now, the remainder is 1 makes sense because f dash x has power here 99.
So we
So
have f of 0 equal to 1 and f of 2 equal to 2, but I don't know how to use it in this case.
now is not the time to use it. You have to use it after you integrate.
Yes, sir.
You have to ultimately think of finding f of x by integration. The main thing to understand is is this correct or is there something else in f dash x? That's what you have to think. We know for sure it has x bar 99 and x minus 2 whole square, but should it have something else also? Q of x plus q dash x. The same polynomial has been written in two different ways. This, the degree of f dash x here depends on the q of x degree. Uh, and here it depends on the r of x degree. And it sort of makes sense that r will have a high degree and q will have a low degree. No, right. R should have a high degree because the same polynomial has to, this means that it has at least degree is greater than equal to 100, right? So yeah, I'm not very sure on this last point here, whether this is allowed or not. Because if we assume that f dash x is this much because of the two factors, then the question is over.
Yes.
Because now we can integrate this, right? So you can find f of x by integrating a x bar 99 x minus 2 whole square dx. And the constant a and the integration constant will be calculated by f of 0 and f of 2, right?
Yes, sir.
So only thing is that I'm not sure whether this part is correct or not. Is there something else with it or not? But I think for that we have to think if a polynomial is of this form, let's say x bar 99 x minus 2 whole square. Then when you divide it by x bar 100, you should get a constant remainder, right?
Yeah.
Because you're getting x bar 101 and x bar 100 terms, right? And one constant to something x bar 99 term, right? Do you understand what I'm saying?
Yes, sir.
If you consider the f of x, f dash x to be this much only, then when you divide by x bar 100, you get a constant remainder. But if there was something else attached to it on the side, some h of x, then you're not guaranteeing that x bar 100 division will give us a constant rate. Do you understand what I'm saying?
Yes. Sir, can we think like this? Like, we can assume that 100 q of x plus x times q dash of x has a 0 at x equal to c.
As a 0 at x is equal to c. What? मतलब why?
So sir, we get a differential equation. No sir, then x equal to c is a constant point, so we cannot use the differential equation. Sorry.
Well, the point I'm trying to say is, if you assume there is something else with f dash x, I don't think the condition 1 and 2 will happen.
Yes.
Because if there is any other polynomial, then the remainder is going to be some degree polynomial, right?
Yes.
Similarly, if I divide this by x minus 2 whole cube, then what happens? If I divide this by x minus 2 whole cube, so you will get something like x power 99 by x minus 2, which is again a constant number. You realize that? This division is basically the division of x power 99 by x minus 2, right?
Yes, sir.
The remainder is 2 power 99, right?
Yes, sir.
Do you understand? At least you are getting constant right now, right? If I had an f of x here attached to it, h of x or something, then when you divide by x minus 2, we don't know whether it will be a constant anymore, right?
Yes.
So I'm still not 100% convinced, but if we assume that f of x is a constant times these common factors, x power 99 and x minus 2 whole square, then obviously we can integrate it pretty easily. You get x power 101 minus 2x minus 4x, so minus 4x power 100 plus 4x power 99. And then you integrate it and you put f of 0 as 1 and f of 2 as 2, right?
Yes, sir.
That will help us solve and find the f of x. So at least one example function we can find. It is not necessary that that is the only function. Right now, I'm not sure about that point, but we can find one function which satisfies it, right?
Yes.
Okay. Polynomials, I don't have anything else to discuss, especially in terms of questions. What we will do right now is couple of classes at least. We'll look at some quadratic equations that also have been asked in your exams. So we'll do a couple of classes on quadratics and then we'll move on to number theory. The next major topic will be number theory, but we'll spend a couple of classes for this. So what I want to discuss here is some standard tricks and standard types of problems that you should be aware of. Obviously, the basic JE level quadratics and all, I'm sure everyone is familiar with. So we'll not spend too much time on that.
Yes, sir.
So let's start with this problem. Let ABC belongs to real positive and they are pairwise distinct. Pairwise distinct. And let A be the set x belongs to real such that ax squared plus bx plus c equals 0. And B be the set x belongs to real such that bx squared plus cx plus a is equal to 0. And C be the set x belongs to real such that cx squared plus ax plus b equals 0. What we have to do is prove that if A intersection B intersection C is not a null set, then A union B union C has exactly 4 elements. Okay, so this is a quadratic question with some set theory. Think about it. The meaning of A intersection B intersection C is not a null set. Basically, that means that there is a common root to all three equations, right?
Yes.
Here, A is the set of roots, real roots of this equation. B is the set of real roots of this one. And C is the set of real roots of this one. So what you can say is that from this condition, we can say that let R be the common root for all three equations. Basically, R belongs to the set A intersection B intersection C. And from there, we can say AR square plus BR plus C is equal to 0. BR square plus CR plus A is equal to 0. And CR square plus AR plus B is equal to 0. Right?
So for r equal to 1, we have all the three equations same.
R is equal to 1 कैसे आएगा? वो हम लोग को पता थोड़ा है रूट क्या है.
हाँ,
We don't know what R is.
right.
We can't make assumptions about the common root. All we know that there exists a real number which is a common root.
So we can multiply equation 1 by b and second by a, and we can subtract beta.
You are doing too much complications. Why don't you simply add all three equations?
Right.
You will get this, right?
Yes, sir.
That's the simplest thing to do, no, here. Then you can see that this part can never be 0.
So a plus b plus c has to be 0.
This part cannot be 0. Therefore, A plus B plus C has to be 0. Therefore, R is 1. Right?
Yes, sir.
So we now know that 1 is a common root for all three equations.
So the other elements will be c by a by b, and b by c. Right.
So now from there, you have to prove whatever you can. Just try it out.
So I was saying that out of 4, we have got one root as 1. So the other 3 can be c by a by b, and b by c.
Hmm. These are the pairs of roots.
Yes, sir. So total we have four kinds of roots.
You have to prove the number of elements of A union B union C is equal to 4.
Yes, sir. And the members are 1 c by a by b, and b by c.
But you also have to show that none of them are equal. No, if they are equal, then it will become 3. No,
Okay.
you have to still show that C by A is not equal to A by B, and A by B is not equal to B by C, and B by C is not equal to C by A, right? And none of them are equal to 1.
So if they are equal, then we will get the discriminant negative. That cannot
कौन
happen.
सा discriminant?
So like we may assume c by a equal to a by b. So we get bc equal to a square.
C
Uh,
by A is equal to A by B. Then we get BC is equal to A square. Then
for some equation, it may come a square minus 4bc. We can find it. So for the third equation, we get the discriminant as a square minus 4bc. So if we get a square as bc, then we get the discriminant negative. That cannot happen.
hmm. So similarly, you can prove the other things also are not possible.
Yes,
So then we know that the number of elements in the union of the three sets A union B union C is 4.
yes, sir.
Okay, so that is the proof. Then the second question, is this one. Prove that for each integer a not equal to 0 comma 2, there is a non-zero integer b such that the equation ax squared minus a squared plus b times x plus b is equal to 0 has integer roots. Any progress?
Sir, we have to take b is equals to some integer times a.
Mhm.
Uh,
Wait, what? B is equal to
a times some integer.
what?
Uh, Sir, because it has integer roots, so I think we do have something like integer root theorem. I'm not sure about the exact statement, but
You
what I
can't
remember.
use theorems which you're not sure about exact statement.
Okay.
I mean, unless you
Yes.
know what exactly you're talking about, how can you say B is equal to A times something?
So like it was something of this kind. The leading term and the constant term, they must like B
That
should
is
divide
called
A or A should divide B.
rational roots theorem.
Yes, so the P should divide B and Q should divide A. I remember.
But if there is a rational root P by Q, then you have that theorem. But
Yes, sir.
right now we need integer roots. So Q is 1. So 1 always divides anything.
Yes,
So
sir.
you don't get anything then. Do you understand? The only thing you get is the root should divide this term.
Yes, sir.
The root should divide doesn't mean A should divide.
Yes, sir, I get it.
So other than that, what is the condition for roots to be integers?
The discriminant should be perfect square.
That is one thing you can try. Or you can try by, let's say, let this equation have two integer roots. Let x1 and x2 be integer roots. What happens if we try to use Vieta's relations now? We get x1 plus x2 is equal to a square plus b by a, and x1, x2 is equal to b by a, right?
Yes.
This is a plus b by a, x1 plus x2, and x1, x2 is b by a. So we can put this b by a here, and we can say x1 plus x2 is equal to a plus x1, x2, right? Then we get x1 plus x2 minus x1, x2 is equal to a. And then there is a trick to factorize such things. You have to add or subtract a minus one. Here, both sides, if I put a minus one,
Yes, sir.
I will get this minus one is equal to a minus one, right?
Yes, sir.
And this can be factorized easily. You get x1, 1 minus x2 minus 1, 1 minus x2.
Yes, sir.
So x1 minus 1 times 1 minus x2 is equal to a minus 1. We are getting, right?
Yes, sir.
Okay. So one possible solution for this would be x1 minus 1 is 1 and 1 minus x2 is a minus 1, right?
Yes, sir.
From where you can say x1 is 2 and x2 is 2 minus a.
Yes, sir.
So if we get this is one possible solution. In this case, x1, x2 product is becoming
4 minus 2. Yeah.
4 minus 2a is equal to b by a. We're getting b is equal to 2a into 2 minus a, right?
Yes.
So always, now you can say here, as long as a is not equal to 0 or 2, for any integer a, we can select a new integer b,
Right.
and that will always be fitting the condition that one root is 2 and the other root is 2 minus a, right?
Yes, sir.
So we don't even have to look for other solutions. Just from this solution, we are getting a relationship between b and a, where as long as a is not equal to 0 or 2, for every time you pick a integer a, there will be a non-zero integer b also, right?
Yes.
That is what we needed to prove.
Okay.
We have come upon the construction of how to make the non-zero integer b, so that the equation always has real integer roots. And the equation has integer roots came by assuming this equation has integer roots, using Vieta's relation and coming up with this condition, which gives us one possibility here, which is this is 1 and this is a minus 1, right? You could try the question in a different way also by taking discriminant is a perfect square. So you have something like a square plus b whole square minus 4ab is a perfect square. But that will be a little harder to analyze.
Yes, sir.
Do you understand what we have done?
Yes, sir.
Okay. Um, the next one is let ABC be positive integers such that B is greater than a squared plus c squared, we have to prove that the roots of ax squared plus bx plus c is equal to 0 are real and irrational. Okay, I'll give 2, 3 problems to try all of them. The next one after this is you have to solve the equation. Solve the equation x power 4 minus 2m plus 1 x cube plus m minus 1 x squared plus 2m squared plus 1 x plus m is equal to 0, where m is a real number. M is a real number, and question 5, let a is less than equal to b less than equal to c be real such that a plus b plus c is equal to 0 and a square plus b square plus c square equals 1. Prove that b square is less than equal to 1 by 6. Try these 3 problems. You have 10-15 minutes, try it out. I'll be back in 5 minutes, okay? Try this. Okay, first one, anything?
So just 2 minutes more for the first one.
Hmm. You have to try to prove by contradiction.
Okay.
Assume that the roots are real and rational, right?
Yes.
First of all, can we first prove that the roots are real? For that, we have to check the discriminant, b square minus 4ac. Uh, we know b is greater than a square plus c square. And they are positive integers, so it will be greater than or equal to 2, right? Because a square and c square will be greater than equal to 1, right? Correct, no?
Yes.
And b is greater than equal to 2, so b square will be greater than 2b, right? We have multiplied the same inequality with b both sides, correct?
Yes, sir.
Are you understanding what I'm saying?
Yes, sir. We multiplied the inequality by b.
And then we can say 2b is greater than 2 times a square plus c square, right?
Yes, sir. And a square and c square, we can use AMGM, so we get greater than 2AC.
You're getting b square is greater than 4ac.
So we have got b square minus 4AC. Yeah.
So basically discriminant is greater than 0, so roots are real for sure, right?
Yes. Yes.
Okay. Now we have to do that. We have to assume roots are rational and get a contradiction, right? Or you could try to prove that roots are irrational directly, but that will be, I think, more difficult.
Yes.
So if A, B, C are positive integers, this is the quadratic and roots are rational, right? So we need some condition in that case, right?
Yes, sir.
So if roots are rational, then b square minus 4ac is equal to k square, right? Where k is some integer
Right.
because perfect square and all. Discriminant should be a perfect square for rational roots, right?
Yes, sir.
Uh, and clearly k will have modulus less than mod b because it is b square minus 4ac, right? And ac are positive,
Yes.
right? So we have already earlier shown that b is greater than 2, by the way, right? And we knew all of this stuff. B square is greater than 2b and stuff, right? We knew
Yes.
that that was greater than 2 times a square plus c square and stuff. All of this stuff we know. So can we say that b square minus 4ac is less than equal to mod b. Just confirm this is true or not. Mod b minus 2 whole square. Just square it, you will get mod b square plus 4 minus 4b plus 4, right?
Yes.
Check whether this inequality is true or not. Basically, for this to be true, 4 minus 4b should be bigger than this. No, should be smaller than this, right?
Yes, sir.
One second. Remove this stuff. You are getting, for this inequality to be true, you need to have b minus ac is less than equal to 1, or b is less than equal to ac plus 1, right?
Yes, sir.
Uh, yeah, I need to prove that this is true independently of this. From here, I want to conclude this, that this is true implies this, which is obvious, but we need to first prove this. So think of this, v square minus 4ac, is it less than b minus 2, mod b minus 2 whole square? So technically we have k square less than equal to this. Basically we are saying k is less than equal to mod b minus 2. Can k be equal to mod b minus 1? Is it possible for it to be equal to that?
So
Oh, it is not possible because
K.
k and b have the same parity.
Yes, sir.
Think about it. Odd even nature, right?
Right.
If b is odd, b square minus 4ac is also odd, so k must be odd, right?
Yes, sir.
And if b is even, the whole thing is even. So k must be even.
Hmm.
So since k and b have the same parity, and k is an integer having modulus less than mod b, right?
Yes, sir.
The next integer it can be equal to is b minus 2, right?
Yes, sir.
So k square will be less than equal to mod b minus 2 whole square, right?
Right.
And then we'll write k square as b square minus 4ac, right?
Hmm.
And from here, this is a correct inequality. So from here we got this, right? Correct.
Yes, sir.
We are getting basically mod of b is less than equal to ac plus 1, right?
Yes, sir.
Okay, and this was under the condition that the roots are rational, right?
Yes.
Okay, fine. Now we will see that if mod b is less than ac plus 1, we know already 2ac is less than equal to a square plus c square. And we know b is greater than a square plus c square in the problem only, right? Correct? No?
Yes, sir.
This was given in the problem. So this is less than b, right? Correct?
Yes, sir.
And we know that b is less than equal to ac plus 1 just now we saw because of rational roots.
Yes, and AC cannot be less than 1.
So from here we are getting ac is less than equal to 1, which is not possible if a and c are positive integers.
Yes, sir.
Correct? No?
Are they distinct also?
AC is less than equal to 1 is coming. So
Yes.
not less than equal to. This is a strict inequality. That's why it is wrong.
Okay.
Because the earlier inequality was This was the strict inequality which made it strict here, right?
Yes, sir.
So there is a difference between 2AC and B, right? B is smaller, B is bigger, right?
Hmm.
So therefore, what we have is not a equal to wala inequality. We have this, right? Which is now impossible. Do you understand?
Yes, sir.
Because of this strict inequality, we have a strict inequality. This was a non-strict inequality, right?
Yes.
So since AC is less than 1 is a contradiction, our rational roots assumption is wrong. So roots are irrational. So there are lots of subtle points here. We'll just revise quickly. So first of all, A, B, C are positive integers. That was given. And what else was given? B was greater than A square plus C square. And we had to show that the equation x square minus A square plus B. No, we had to show that the standard equation ax square plus bx plus c has real and irrational roots. So what was the first thing we did? We first showed that b is greater than a square plus c square, which is
So,
clearly greater than equal to 1 plus 1. So we got b is greater than equal to 2, which got us b square is greater than equal to 2b, which got us greater than 2 times a square plus c square,
and
which
then we
is
use,
greater
yeah.
than equal to 4ac, and which gives us discriminant greater than equal to 0. Greater than 0, right?
Yes.
So that gave us roots are real, right? Then
Yes.
second thing is we assume roots are rational. Assume roots are rational. And if we assume that, then b square minus 4ac is equal to some k square, some integer, right?
Yes.
And from there we got k is less than mod b, right? Because this is positive,
Yes.
correct? And also we got k and b have same parity, right?
Yes, sir.
And if k and b have the same parity, then k will be less than equal to mod b minus 2, right? Cannot be equal to mod b minus 1 then, right?
Hmm.
And from here, now we can say that k square is less than equal to mod b minus 2 whole square. And k square was equal to b square minus 4ac less than equal to mod b minus 2 whole square. And from here, we concluded that mod b is less than equal to ac plus 1, right?
Yes, sir.
Once we have mod b is less than equal to ac plus 1, now we will use the fact that now we will get a contradiction on the original equation. We will say that we have 2ac is less than equal to a square plus c square, and that was less than b, and that is less than equal to ac plus 1. So that implies that AC is less than 1, which is a contradiction. So the roots cannot be rational and must be irrational. Is it clear?
Yes, sir.
Okay, so tricky problem, but you need to know there are so many things that are possible because A, B, C are positive integers and because of this condition, right?
Yes, sir.
Okay, next one was the quadratic equation, not quadratic, fourth degree equation. Try it out. M is real and we have to solve this equation.
Okay.
So what is the idea here? Obviously, you cannot try to solve the fourth degree equation.
Yes, sir.
Don't try that. You will not succeed. The idea is that you have to use this condition and think of this as a quadratic in M. Do you understand what I'm saying?
Yes, sir. And we can use the real root condition, right?
Hmm. If you rewrite the equation as if a quadratic in M, you will get something like this: x squared minus 2x cubed plus 1m plus the other terms will have just x. Right?
Yes.
And from here, we'll check the discriminant of this must be, since it is real, must be positive, right? Discriminant will be x squared minus 2x cubed plus 1 whole square minus 4 into 2x. So 8x into x power 4 minus x cubed minus x squared plus x, right?
Yes, sir.
So one thing to notice here,
X equal to minus m we can put, I think.
x equals to minus m. Right. Why would you put that? This is what we have. Um, you have to simplify this a little bit, because if you don't simplify this, it won't, you'll not understand what we'll do with this. So probably you'll have to open it up and see what is coming. So let's do that. X
So
power
a little
4.
factorization can be done in 8x square into x power 3 part, that part. We can take x plus 3 plus 1 as one pair
uh,
and the other one as.
you can do that, but it doesn't help us much. Maybe you can factorize this also with x plus 1, x minus 1.
Yes, sir. So if we take some things common, then I think by cancellation. Simple.
You can try it, but I want to expand this. Let's expand it a little bit. Minus 4x power 5 minus 4x cubed plus 2x squared minus 8. Is it a minus 4x power 5? Yeah. Minus 8x power 5 I'm getting here. Plus 8x power 4 plus 8x cubed minus 8x squared. So ultimately I'm getting x power 4x power 6 and x power 4 will combine. So you have minus 12 x power 5 and this is gone, this is gone, this is gone. X power 4 is here and here. So plus 9x power 4. And then x cube is here. So plus 4x cube. And x squared is minus 6x squared plus 1. This is what we are getting, right? Okay. All the even powers we will keep together, like this even power, this even power, and this even power. Focus on them. And you can think of them as 2x cube whole square plus 3x square whole square plus 1 square. And now notice that minus 2 into 2 into 3 is minus 12x power 5. And we have a plus 2 into 2x cube into 1 this term. And minus 3x square into 2 into 1 is this term. So it's a perfect square, by the way. Del is basically 2x cubed minus 3x squared plus 1 whole square. Do you see how it is becoming that?
Yes, sir.
So because it is like that, what we get now is that the roots will come easily now, right? M will come out to be like, you will take this outside the root and you'll be able to solve it a little bit, right?
Yes, sir.
There will be two roots for M. One will be x square minus x and one will be x square minus 1 divided by 2x. And then you have to think of these as two separate quadratics. Do you
Okay.
understand what I'm saying?
Yes, sir.
Now it will be a quadratic in x, right?
Mm.
And you will get the answer x in terms of M later.
Yes, sir.
That is the way to solve this question 4. You need to try question 5 later. Try it. Tomorrow we'll continue with more problems.
So for the third one, like what I thought, may I discuss?
I have another class starting, so I can't discuss right now. But
Okay,
tomorrow we'll discuss the solutions.
okay. Thank
Okay, fine. That's all for now.
thank you.
Mhm.